Hello. So I would just like to say a few things about Kasumu Section 1.3. First, a definition. Let P sub k super n is the probability that xn equals k. That's the probability that the system is in state k at time n. Remember, the system moves from state to state. It's always at a definite state at each step during the chain. So here we're looking at the state of the system after n steps. We can also define this quantity P sub jk super n, which is the probability that if you start in state j, the system is in state k at time n. I would just like to say that because of the stationary Markov property, this is not just the probability of starting in state j at time 0, it's starting in state j at any time, then the system is in state k at a time n steps later. So we could say this is the probability of transitioning from j to k in n steps. Now again, please notice there's an ambiguity between the capital P and the small p. The usage is not consistent. This capital P sub k super n is the same as this P sub j super n. So here we're investigating the probability of being in state j at time n plus 1. How does that relate to the probability of being in various states at time n? Well, you are in some state at time n, and then you have to transition from that state to state j in one step. Well, that's expressed by this equation 1.3 here. I have a certain probability of being in any step I at time n, and then from that state I need to transition to state j. So the probability of being in state j at n plus 1 is the sum over all states I of the probability of being in states I at time n times the transition probability. Now, in fact, this is just matrix multiplication. Let's write this P super n as a vector in which each component gives the probability of being in each different state. So this is the nth step probability distribution. So this equation 1.3 actually says that to get the n plus 1 step probability distribution, you multiply by the vector nth step probability distribution times the transition matrix. Notice the single underline for the vector and the double underline for the matrix. Now we can repeat this process. This vector Pn can be derived from the previous state, which is Pn minus 1. So it's the vector Pn minus 1 times the matrix P. And Pn minus 1 can be derived from Pn minus 2, and so on, so on, so on. You can work all the way back to P0. So the probability distribution at step n plus 1 is the initial probability distribution times the transition matrix raised to the n plus 1 power. So this is just matrix multiplication. Now from this matrix multiplication, we can derive some useful properties. On the next page, we have the Chapman-Common equation. It looks rather complicated. But in fact, all this is saying is that the n-step transition matrix, which we know is the product of n copies of the single transition matrix, can be broken up in various ways. If I take the transition matrix raised to the nth power, I can separate off r power times the n minus r power. And that's really all that this equation is saying. After this, the rest of the chapter just gives some examples. So let me move on to section 1.4, stationary distribution. Now, typically, the probability distribution will change over time. But in some cases, you may have a probability distribution that does not change from time to time. That does not mean that the chain stops moving around. The chain state will change, but the probability distribution of the state will not change. You can think, for example, of a sequence of coin flips. When you take a sequence of coin flips is a Markov chain, and the probability of being head or tail at the next flip is half-half. That probability does not change. However, the actual value of the coin flip will change every time you run the process. So please make sure that you have the distinction between probabilities which do not change and states which change even though the probabilities do not change. So this equation we've seen before, that the nth step probability vector is the n minus 1 step probability vector times the transition matrix. Now, in some cases, the distribution will settle down to an equilibrium distribution that does not change. So we would call this the limit of Pn as n goes to infinity. We call that pi. Now, if we take the limit on both sides, this pi must satisfy pi equals pi times the transition matrix. Now you may recognize this as an eigenvector equation. Pi is an eigenvector of the matrix P. Now you may be used to seeing eigenvectors multiplying the matrix on the right-hand side. Those are called right eigenvectors. This is now a left eigenvector. And the eigenvalue for this eigenvector is 1, because you have pi times the matrix equals 1 times pi. So the stationary distribution of a Markov chain is an eigenvector of the transition matrix with eigenvalue 1. So the next page gives some examples of stationary distributions, which are eigenvectors with eigenvalues 1. You're just solving an eigenvector-eigenvalue equation. And since you know the eigenvalue is 1, that simplifies the process. Basically what you're doing, as you can see in this example, is you write the eigenvalue equation like this, and you bring this vector to the other side and combine it with the vector here. So in fact, what you're solving is this matrix pi times the transition matrix minus the identity matrix is equal to 0. So you're solving a homogeneous system of linear equations. So you can read through these examples. More examples on this page. Now there are some theorems about eigenvalues of stochastic matrices. Remember, a stochastic matrix, the way we're defining it, is a matrix whose rows sum to 1 and whose entries are non-negative. And it turns out that all eigenvalues of such a matrix satisfy absolute value of the eigenvalue is less than or equal to 1. And such a matrix always has an eigenvector with eigenvalue 1. Another useful fact is here, you may know that you can typically diagonalize a matrix using this matrix Q. B equals Q inverse PQ, where B is a diagonal matrix. You can move the Q's to the other side and write P equals QBQ inverse. Then the nth power of P is Q times B to the n times Q inverse. This is a fast way, a convenient way of computing the nth power of a matrix. This works in general for general matrices. It works in particular for stochastic matrices. So here he goes through the usual process of finding the eigenvalues, then finding the eigenvectors. The eigenvalues give you the matrix B. The eigenvectors give you the matrix Q. That enables you to write P as QBQ inverse. And once you have Q and B, you can easily find the nth power. Okay, so that's a brief overview of sections 1.3 and 1.4.